Okay, so let's talk about continuity. So you guys may have had some continuity stuff in pre-cal, maybe not. Anyway, this is kind of a rehashing of that. But a continuous function is one that has no breaks. And the way that I define breaks is basically if I'm going to draw a function and at any point if I have to lift my pen up off the page, then at that point where I had to lift my pen up, the function is not continuous. If you look at this in that outline I just traced to that function, you notice that when I draw it, I could draw this without ever having to lift my pen up off the page. Therefore, this function right here is continuous. Now this function right here, if I'm going to draw the lines here, immediately when I get to this vertical asymptote, I have to lift my pen up off the page to bring it down to the next part. Additionally, right here where we got the open and closed circle, I have a jump here where there's no way I can go from here to here without lifting my pen up off the page. Same thing here, to put this little hole here, I just lift my pen up off the page for just a brief moment and then continue to draw that function. So that's kind of the rule of thumb that I like to use to teach people about continuity. But there's a slightly more mathematical explanation of continuity, and that's that a function, call it f of x, is continuous at a point x equals a if the function evaluated at that point x equals a is equal to the limit of that function as x equals a. Now this might sound kind of bizarre and kind of confusing, but just listen to me real quick. Let's pretend that point a was right here and that f of a was equal to 1 right there. Well, in this case, we know that point would be continuous because if we evaluate the limit as x approaches a, from the left and from the right, we're approaching that y value equal to 1, and the function value is also equal to 1. So since the two things match up, that's continuous, all right? And let's look, for example, at this part right here. If this value, let's say that was equal to 1, and this was right on 0, well, as we approach this point, let's call that the point A. If we approach this point A from the left, well, we're going to 1. If we approach that point A from the right, we're going to 0. So therefore, the limit would not exist right here, but the function value would be right where this closed circle is, which is at y equals 0. So in that case, we would have a mismatch where the function value would not be equal to the limit. So therefore, that's not a continuous point, okay? So let's look at the three main types of continuity or discontinuity that we're going to talk about in this class. There's another one called an oscillating discontinuity, which if you want to know about that, just ask me and I'll tell you about it. So the first one are called removable discontinuities. We also referred to these in previous videos as holes. So this is where you just have a little hole in the function right here. So for example, if we were to look at this function and I asked you, what is the limit as x approaches 1 of f of x, what would you tell me? Shout it out. Okay, hopefully you said that limit would be 1 because from the left and from the right we are approaching 1. However, if you asked me what f of 1 was equal to, what would you say? You would say 2 because that's where the closed circle is. So in this case, the limit is not equal to the function, so therefore this is a point of discontinuity. Now another form of removable discontinuity, we don't need to have that closed circle right there. We could just have straight up a hole, which is like some of the examples we looked at in the previous videos. So in this case, if we looked at this example, the limit of f of x as x approaches 1 would still be 1, but f of 1 in this case, if we have a hole right here, what does that mean f of 1 is? Well, it means f of 1 is undefined. So we don't know what that is. It's question mark. I would write undefined, but obviously I don't have enough space. That's what happens when you improvise these things, people. It all goes off the rails. All right, so the second type of discontinuity we could have is a jump discontinuity. That's what occurs when basically instead of having a little hole in the function just jumps. A lot of piecewise functions have jump discontinuities. Like one good example of one, I think at least it was a couple years ago, like the tax bracket breakdown has a couple discontinuous jumps in there, I think. But anyway, so in this case, let's say this point was 1, this x value was 1, the y value was 1, and this y value was -1. Now, if you asked me in this case, what is the limit as x approaches 1 of this function, you should tell me that that limit would be does not exist. So why would the limit not exist? Well, the limit would not exist because if we looked at the function approaching from the left, if we looked at the limit as x goes to 1 minus, we would get negative 1. And then if we looked at the limit as x goes to the right, so as x goes to 1 plus, that would be equal to 1. Negative 1 and 1 are not the same thing, therefore the overall limit does not exist. However, if I asked you what is f of 1, you would tell me, well, that's equal to 1 because that's where the closed circle is right there. So again, in this case, we get that the limit is does not exist. The function at that point is equal to 1. Does not exist and 1 are not the same thing, so therefore by this theorem, that's a discontinuous point. All right, so the last one is an infinite discontinuity, and you can go over the exact same type of analysis that we used for this one. But for example, if you looked at the left-handed limit as we go from 1 to the left, this one would be going to positive infinity. To the right, it would be going to negative infinity. And at the point x equals 1, our function is undefined. This is a vertical asymptote. We could have a hole right, or a filled-in hole right there if we wanted to, but that would still be a discontinuity because even if we had that hole, f of 1 would be 0, and the limit would be does not exist, and 0 and does not exist are the same thing. Okay, so that's just a brief breakdown of types of continuities we can get, and a couple examples right here. We didn't go over this one, but you can do this one on your own and get the same results. Kind of just how we use limits to evaluate if a function is continuous or not.